Today we are going to discuss the vapor liquid equilibrium, the second topic, the second lecture of this topic, and that is related with the vapor liquid equilibrium, the special case of the vapor liquid equilibrium, and that name is the azeotropic vapor liquid equilibrium. It is a very special type of the vapor liquid equilibrium data that gives a typical, totally slightly different from the TXY data as we have discussed, as we have studied in the previous one, that is a common VLE data. So what is the meaning of azeotrope? Azeotrope, the meaning is basically that it is a constant boiling point mixture in a mixture of two or more liquids whose proportions cannot be altered or changed by a simple distillation. So this is the meaning of azeotropes, means it is a constant boiling point mixture. Alternatively, you can also explain in some other words that it basically, when this type of mixtures boils, what happens? The vapor, the composition of the vapor that vaporizes from the liquid have the same proportions and same compositions of the constituents as the unboiled, that is as the liquid mixture. So it means that the vapor composition is same as the composition of the liquid. There is no change, means the vapor composition is same as the liquid composition. So there is no change in the vapor and liquid, and that's why we call it as a constant boiling point. So there is no difference. It is just like a pure component. Just like a pure component means, for example, water is a pure component. It boils at 100 degrees Celsius. And the mixture, water and methanol is a mixture. Water and ethanol is a mixture. But if it is also boils as a constant boiling at a one single boiling point, so that is totally different from the common phenomena of the mixtures, because the mixtures are not boiling. They have 2 points. One is bubble point, one is dew point. But in the azeotropic type of mixtures, they have one single point that is called the constant boiling point. So at that position, the vapor composition and liquid composition both are same. That's why the separations is not possible at this position. So there are two types of the azeotropic mixtures. One possibility is the minimum boiling or the positive azeotropic mixtures, and the second is the maximum boiling or the negative azeotropic mixtures. Example, ethanol water. Ethanol water is the example of the azeotropic mixture. Now let us look a brief about these two types of the azeotropic mixtures. The first one is the minimum boiling or the positive azeotropic mixtures. If you look at the TXY diagram, this is a TXY diagram, this is the XY diagram, and if you look about the TXY diagram, temperature and compositions of X and Y both are given here. So if you know the X, you can find the Y value, and this is the liquid as the simple TXY. This is a vapor, and obviously in between these envelopes, this is a liquid and vapor. So what happened? If you see, this is the diagram, this is the diagram of the saturated liquid, and this is a diagram of the saturated, this is a diagram of the saturated vapors. Sorry. Okay, so what happened here? At this point, saturated vapor and saturated liquid envelope is approximately equal, and there is no difference between these two one, and that's why it is called the constant boiling. At this temperature, this is the temperature at which this mixture boils at the same compositions. So this is the point, and this is because this is appears at the very lower level, at the minimum level. That's why it is called a minimum boiling azeotropic mixture. And if you look about the XY diagram, this is a X value, Y is equal to X line, Y is equal to 45 line basically, and this is equilibrium line, and this is equilibrium line. If you see at the starting level, it is greater, Y is greater than X, but after some times it is now less than the liquid, and this is the point where the constant boiling point occurs. So this is totally the different, have you seen that this is totally the different type of the graph as compared to the conventional XY and TXY diagram. Come to the second position, that is the maximum boiling or the negative azeotropic mixture. If you look here, you will find that this is the temperature where both envelopes are coincide with each other, and there is a constant value of the temperature. That's called the maximum boiling temperature. And if you look at the XY diagram, the same thing is also shown here. At the starting, this is the diagram, and at the end, you will see the diagram is this one. At this point means this is a point where both compositions are same. There are no difference between the liquid phase and vapor phase, but before that vapor phase and liquid phase is different, and after that vapor and liquid phase have a different values, but both have a totally opposite sign. Means at this case where the vapor composition is more, liquid composition is more as compared to the vapor composition, and these conditions vapor composition is more as compared to the liquid composition. So this is the azeotropic mixture. Now come to the second topic that is required to know you, that is how the VLE is affected by the pressure. If you provide the pressure, we know that these diagrams are basically developed. This is a diagram. This diagram is developed at a constant pressure. But if you increase the pressure, for example, this is at 1 atmospheric pressure, and if you increase the atmospheric pressure as 10, so what happened at 10 atmosphere? So that is the question here. So it's a simple here the P2, this one is a P2 and this one is a P1. So in our case the P2 is greater than P1, and what is happening, what you can observe here, the vapor liquid equilibrium temperatures are higher at P2 than the P1. It means that this value, this temperature value is higher for this case, means it is not vaporizes at a lower temperature, it is vaporized at a higher temperature. So this is the observation that is basically you have to look. And the second observation, the equilibrium phase lies as the high pressure are usually closer together, means the envelope, this envelope that is formed here, this envelope is very much wide as compared to the high pressure. I mean at the high pressure what happened, the envelope is close, and if you increase further the temperature, the envelope is much more close. So this is the difference, means at the lower pressures more differences and more distance are there in the envelope. And as we know, and you all should remember that more, if there is more difference in the envelope, the separation becomes more easy. So that's why this is desirable things. So this is the effect of pressure. Now come to the second very special type of VLE graph. This we all know that this is a TXY graph, and this is called, if suppose here in this case in the TXY graph pressure is constant, but you can also draw the PXY graph where the temperature is constant. So for the same composition, if you look here, that both things are slightly different. This is the the initial boiling point, or the boiling point of a pure component of B. This is a pure component of A boiling point, and these are the liquids and these are the vapors. These are the vapor plus liquid. This is known as a saturated liquid, saturated vapor, and so on. And if you come to the pressure, this is a pressure line, and x-axis is the composition. This is a vapor and this is a liquid. And if you increase the pressure, the things are going into the liquid phase. And this is a saturated liquid, and this is a saturated vapor composition. This is a vapor plus liquid composition. So it is slightly different from the TXY diagram, and this is the basically the pure component of the A, and this is the pure component of the B. So this is all about how the VLE diagram looks like for the different types of the cases. When the azeotrope mixtures are there, how it looks like. When the pressure is high, how it looks like. And when we are not developing TXY but PXY, how it looks like. So thank you very much for all this one.